Good afternoon, everyone, and welcome to this year's Christmas lecture organized by the Open University School of Mathematics and Statistics. Our special guest today is Zoe Griffiths, who will talk to us about the exciting topic of freaky probability. And I am Kaustup Adhikari, a lecturer in statistics at the Open University, and I will be the host of today's event. Due to the pandemic, we could not host this event face-to-face this year, but thank you all for joining us online for this event, either through Zoom or if you're listening to YouTube. And special thanks to all the teachers who are hosting this session for their students. And before I hand it over to Zoe, a few housekeeping items to remember. This talk will be about an hour long in total, with some time for questions at the end. And I need to let you know that this lecture is being recorded. The recording will be available only to university staff and to schools who have signed up for this event but could not make it. It will not be shared outside of this. And in general, if you're attending, your video and microphone will be kept mute, so you won't be seen for the recording anyway. If you have any questions during the talk, please send them to us through the Zoom or YouTube chat system, and we'll compile them and ask those to Zoe at the end. But throughout the lecture, if you want to get in touch with us for any reason, you can also do that via the chat box. For example, if there is a technical issue with the audio, you can't hear us, please let us know about that as well. And Zoe will be sharing slides through her webcam. So it's best if you adjust your Zoom settings accordingly. We are giving the instructions in the chat box, but very briefly, please select gallery view and turn the hide non-video participants option. Turn the hide non-video participants setting on in Zoom. And the instructions are in the chat box. But for those who are watching us on YouTube, you don't have to change anything. And you will be kept off on your video and microphone during the talk. But if you are a volunteer who is going to interact with Zoe, then we will turn your video and microphone off when that section starts, and then we'll turn it off again. And there are several interactive things that students can do on their phones during the talk. And so we will refer to them at specific points. And the links for those the links will appear on the screen for those interactive sessions. And they're very brief things, so you can just type them from the screen onto your phone. And we know that some students are going to join us individually, but most students will attend in groups supervised by their teachers. So in that case, I would request the teachers to please send us their students' questions for Zoe at the end. And students can join into those interactivities via their own mobile phones or devices, of course, with the teacher's permission. And we'll compile all your questions, and Zoe will answer them from the chat box at the end of the lecture. Now, without further ado, I would like to introduce our guest speaker for today's session. Zoe Griffiths is a mathematician who used to be a secondary maths teacher and now travels the country and the world, talking about maths in schools, in science festivals, and even on BBC Radio. So over to Zoe for a very interesting tour of freaky probabilities.
Okay, perfect. Thank you very much. Hello, everybody. So as you've heard, I'm Zoe. I'm very excited to be doing your Christmas lectures this afternoon. Probably the easiest way to explain who I am is to say I'm a mathematician, and I spend a lot of my time going into schools, as you've heard, talking about maths. So I do talks and workshops, although actually I say going into schools at the moment, less going into schools physically and more doing this sort of thing virtually, as you can imagine. But I don't just do stuff for schools, so I also talk at science festivals and in the media. I've talked about maths on BBC Radio. Pretty much anyone who will ask me to talk about maths, I will do that. So that's what I do. I used to be a maths teacher, actually, and like your maths teachers, I started being a maths teacher because I wanted to kind of share my enthusiasm and my excitement for maths with other people. And now I just get to talk about whatever I want. So I don't have a curriculum, which is kind of exciting. Just get to choose the bits of maths that I find most exciting and most interesting and make talks and workshops about them. And today is definitely one of those. So I'm talking about probability, as you've guessed, if you've seen the title of this talk at all. And that's because it's one of my favourite topics. If somebody says you can talk about whatever you want, I will say probability. That tends to happen. And it's one of my favourite topics because it's not always what we see. So it's not always what it seems. So it's called freaky probability. And the reason for that is there are various points in our lives. And when we ask ourselves the questions, what's the chance of that? What are the chances of that happening? And we kind of think that, we think the odds of something happening are one thing, and mathematics tells us something else. So there are lots of times in life where our intuition about the chances of something happening in life or in games and that kind of thing does not agree with actually what mathematics says. It's an interesting topic with lots to explore. So freaky probability, it's about those moments when you're looking at probability that are counterintuitive. And so we're going to be exploring counterintuitive probabilities via a series of audience games. So you're going to be playing some games, and in each case you're going to work out what your chances are of winning those games, and then have a think about whether that is intuitive or not. Does it agree with our intuition or not, or is it freaky? Is it slightly strange? So that's the title of the talk, freaky probability. So a series of games, and we've got an awful lot to pack in, so we're going to get going with our games. But actually, before we play our very first game, I would like to introduce you to a very good friend of mine who is here with me, and that is, of course, my very exciting lottery machine. Here we go. So this is my lottery machine. Quite possibly the world's smallest lottery machine, but that's okay, because we are going to be playing a micro lottery, a mini lottery, not a normal sized lottery in the talk today. So the real national lottery, as I'm sure lots of you know, you choose 6 numbers, and you choose 6 numbers from 59. So 59 is the number of options you have, and you choose 6. Whereas in my micro lottery today, I've got 10 numbers in the basket of this machine, and you're choosing just 2 of them, right? So it's a micro lottery machine, all very appropriate. And I say you're going to be choosing 2 numbers. Actually, you have already chosen 2 numbers. So when your school signed up, you were sent a link to go and fill in a Google form to choose your 2 numbers a couple of weeks ago. And so if you've chosen your 2 numbers on the Google form, that's closed now, so you can't fill that in anymore. And it's closed so that I could process all of the entries that we had. And already on my spreadsheet, I have got the winner for each of the different possible combinations. I've got the winner ready to tell you at the end, based on what the 2 numbers are that come out at the end of the show. So we'll be doing the draw at the end of the show, and then we'll look to my spreadsheet to see who the winner is. And I say the winner because if there are multiple people who get the 2 winning numbers in the lottery draw, then I have randomly, I've put you into a virtual hat in my spreadsheet, and my spreadsheet has spat out one person randomly who is going to be the winner. So there is one winner who can receive a mathematical prize by post. But obviously, if you haven't chosen your numbers, if you didn't get around to that, or you haven't been sent the link, you can still play along. So you can jot your 2 numbers from 1 to 10 down now, so 2 whole numbers, 2 different whole numbers from 1 to 10, and then at the end you can see how you do. And you won't be able to win a prize, but you will be able to win pride, which, I mean, everybody knows is a much more long-lasting and significant gift than anything I could post to you in the mail. So you can still take part. And I say 2 different numbers, and that's because at the end of the show, when I do this, I will draw out 1 number from the basket and I'll show it to everybody, and that'll be your first number. And then once that number has come out, it will stay out of the basket. That's why you have to choose 2 different numbers. And then we'll choose a second number, and we'll see what that one is. And that's pretty much it. So if you choose or chose the same 2 numbers that come out of that basket later on in the show, in whatever order, it doesn't matter what order those numbers come out of the machine, then you have got the winning numbers, which is very exciting. And you might be somebody who is getting the mathematical prize at the end of the show. So that's the idea. So we're coming back to that at the end. We've got a lot to do before that happens. And so we will play our first game to get us going. So our first game is going to involve you choosing something. So I'm going to show you on my screen 8 options, and you've just got to jot down on a piece of paper, or remember in your head if you don't have any paper, which of these 8 sequences you would like to choose. So these are the 8 things that can happen if you flip a coin 3 times, right? These are the 8 different outcomes. If you're not convinced about why there are 8, that's something you can go and have a think about afterwards, but there are 8 different outcomes if you flip a coin 3 times. Just choose one of them. Literally going to give you like 10 seconds to do that. So just choose which one you would like. And actually, while people are choosing this, I'm looking at the chat here. So basically, I've got two devices. And if you see me looking over here, that's because I'm looking at the chat box. So if you put anything mathematical in the chat box, I'll try and have a look at some point. It's quite tricky for me to look at the chat whilst I'm also showing slides and talking and stuff. So when I'm asking you to investigate something or do something in this talk, that's when I'll have a quick look at the chat. And see if there's anything that I need to address. I think that's pretty much it. So hopefully you've now had time to choose your sequence, the one that you'd like. And I will explain how this game is going to work. And I'm going to explain this game for about a minute. And then after that minute, I'm going to ask, I've got a volunteer ready in the wings to be my coin flipper. And that person is Angie. Angie doesn't need to come on just yet. So I'm just going to talk for a minute. So Angie, this is your 1 minute warning that I'm going to need you in a minute. So the way this game works is you've got two players and each player choose one of the two sequences. One of the 8 sequences. So you can see you've got 2 different sequences here in yellow. And then we flip the coin until one of these 2 sequences comes up in a row. So for example, let's imagine we flip the coin and we get these as our outcome. Now you can see that neither of these 2 people have won because neither of their sequences matches HTH exactly. So nobody's won yet. So we need to keep on flipping that coin until one of these 2 sequences comes up. So I'll keep on flipping that coin, and I don't know, let's imagine this happens. And now you can see the person on the left has won because their sequences come up consecutively and they've won that game. So that's the idea. You just keep on flipping the coin until one of the 2 sequences comes up. So that's the game, but I thought it would be a little bit boring if I played against just one of you. There are a lot of people watching, so I've devised a way that I can play against all of you at the same time. This may or may not work, we'll see how it goes. So you have already chosen your response, and based on what your response is, I've decided what I'm going to play against you, which you can see on the screen now. And so, for example, let's imagine you chose tails, tails, heads. That means I've decided to play heads, tails, tails against you. And so what you'll need to do is you'll just need to keep an eye out for both of those sequences during the long string of coin flips and see which sequence comes up first. But your game, the one that's circled, is not the only one that will be happening. There are another 7 games going on simultaneously at the same time. So there's quite a lot to keep track of, but it will make a lot more sense once we actually start playing. So just have a look and see what sequence I'm playing against you, so you can keep that in your head or jot it down if you need to see which sequences you're looking out for. So that's the game. I'm now going to invite Angie to come onto the virtual stage. And so Angie, you are my coin flipper, I believe. Are you ready? Have you got a coin there that you're ready to use?
Oh, I've got a coin here, Zoe.
Perfect, excellent. So I'm just going to stick my board on my camera and hopefully we can all see that. Excellent stuff. Okay, that's fine, I think. Let's move it this way slightly. So Angie is my coin flipper. She very kindly volunteered to flip our coin today. And so what will happen is that Angie will flip the coin and I will write out what happens up here. So let's imagine that the first one is heads. Then I'll write an H there, and let's imagine the second one is tails, and we'll get a T there. And then H for heads again, whatever. This is just an example, obviously. And once I've done 3 of them, we'll then stop for a second and we'll see if we can see heads, tails, heads on the game board. So this is just the same thing as I just showed you on the slide, but handwritten. So heads, tails, heads. That appears here. So you just chose heads, tails, heads here. So that means you've just won that game there. So I'll dot it to show that you've won it. And I will cross myself out over here to show that I've just lost that game. And then we just keep on going. We're going to keep on going until we've resolved all 8 games and see how many I've won and how many of you've won. So let's imagine the next one was like tails. I don't know, that's an example again. Then the next 3 we'll be looking for is tails, heads, tails. And that is here. So you chose tails, heads, tails here. So you would have just won that game. Hopefully this is all making sense. And that means I would have just lost this game. So I'd be crossing myself out over there. A little word of warning. I have never lost this game, and that includes this morning's talk. So I've probably played this maybe 40 times, something like that, and I've never lost this game. But that doesn't, I mean, it's the first time for everything, doesn't mean you're definitely going to lose. When I say I've always won, I've always got 5 or more of the 8 games in my favour. So you could be the audience to break me. Let's see what happens. See if you can beat me. Are you ready, Angie, with your coin?
Certainly am. Here we go.
Okay.
Ready when you are.
Yep. Good to go.
Whee! That tails.
Fabulous. Okay, we've got a tails. Oh, my pen is running out.
Tails again.
I'll change my pen while Andy keeps flipping. So tails and then tails again. Yep.
Tails again.
All right, we'll stop there. So we've got tails 3 times in a row. We will stop. So tails, tails, tails. So you chose tails, tails, tails here. So you have just, I'll get rid of my examples. Don't want to give you extra games for free. They were examples. So tails, 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 you've just won. And that means I've just lost. So sometimes you're in the lead, 1-0. That could be your day. Who knows? Right, next one.
Heads this time.
Heads this time. Okay. So we're going to stop. So tails, tails, heads. You can get the next coin flip ready while I'm doing this if you want to, as long as you don't tell us. So tails, tails, heads. So you chose tails, tails, heads here. And so excellent work. So I've just lost. You've just won. Oh my gosh. But I chose tails, tails, heads here, didn't I? So I just chose it here. So I've just won that game, and I've won that game. Which means you have just lost 2 games. So we are even Stevens, right? It's all square at the moment. Next one.
Next one. Tails again.
Tails again. I'm changing to green because I'm running out of pens at quite some rate today. So tails, heads, tails. So you chose that here, but you have already lost, right? You've already lost tails, heads, tails there. So we can't do anything. So let's keep going.
Heads.
Heads. Heads, tails, heads. You chose heads, tails, heads here. Oh my gosh, this is not good. You are winning. So you've just won that game and I've just lost. Okay, let's keep going.
Sorry about this, Zoe.
That's all right.
Heads.
Heads. At least everybody knows it's not a fix. Angie is not a plant. This is genuinely happening. Because if I lose, I'll be very upset. Was that heads again, did you say?
It was heads, yes.
Okay, perfect. So tails, heads, heads. You chose that here, but you've already lost with that. It's looking okay. It's okay. It's back in the game. So tails, heads, heads. So I had tails, heads, heads here, and I had it here, which means I've just won those 2 games at the bottom. Hopefully you can see that green crossing out. I think that's okay, isn't it? So I've just won these 2. So I've got 4 and you've got 3. So it's 4-3 at the moment. Will it be a draw? Okay, next one.
Heads.
Heads. Okay, so that was heads, 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 which you had down here, but you've already lost. Let's keep going.
Oops. Tails.
Tails. So we've got heads, heads, tails, which you... Oh my gosh. Oh my gosh. What has just happened? No, that's wrong. That's heads, tails, tails. Oh, phew. Thank gosh for that. Heads, heads, tails. I thought you just got that one. Heads, heads, tails you've already lost with. And I've got heads, heads, tails over here. So I'm afraid to say I have just won that final game, and I have got 5 and you have got 3. You were very close to breaking my winning streak. Thank you very much. Can I have a round within your own sort of vacuum of your classrooms, because your mics aren't on, that's fine. Can you please give Andy a round of applause for excellent coin flipping work? That was great. And we'll have a think about this game, think about what's going on. And so in this game, I've got 5 and you've got 3. So you could probably think, well, maybe I just got lucky, because 5-3 isn't an amazing win. But I'll tell you, this morning I won 7-1. And I have won this game every single time I've ever played it, which actually is kind of lucky. Like I've got luckier than I should have done. And I've probably played it, I don't know, maybe 30 to 40 times, something like that. So given that information, I think some of you will be thinking there's something weird going on. This is a fix. And it's not a fix in the sense of, like, I haven't cheated. Angie genuinely was flipping that coin. So it's not a fix in that sense. But I do have a strategy, right? There is something going on. I didn't just get lucky. And I want you to see if you see any patterns in the outcomes that I chose. So I'm just going to go back to my slides so it's easier to see. So on the slide, you can see what I chose and you can see what you chose. Do you spot any patterns in what I chose or I didn't choose that you think maybe might explain the strategy? Now, if you think you've seen this before, don't just tell everyone in the chat exactly how it's done, because let them think for themselves. But if you see any patterns that you think might be helpful to know about, then stick them into the chat. So whether that's a teacher getting feedback from your students or whether that is a student themselves, just stick into the chat anything, any patterns that you see. And I'm probably going to give you like a minute or something to do that, and I'll keep an eye on the chat. So what patterns do you see? Okay, is everyone having a think about it? I think we're not got anything in chat at the moment. Oh, somebody's got a couple of comments. I'm going to read them out as we go along. You have got more time to think about it, more time to discuss, more time to write into the chat, but as they come in, I'll start telling you what I'm seeing. So it says you have 4 pairs of combinations. We had 8. Very nice observation. That's from David Johnson. So I had 4 pairs, and actually you can see those pairs quite clearly when you look down the blue list. So I've got heads, tails, tails together, then I've got another pair that are the same, and then another pair that are the same, and another pair that are the same. So I wonder what that's got to do with something. So I've got 4 pairs that are the same. So teachers, if you want to get some ideas from your students and pop them into the chat, that'll be great. I'll give you about another half a minute or so. Okay, and Kerry says you don't have any sequences of 3. I do not. So I have not chosen tails, 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 or heads, heads, heads. Is that the only ones I've not chosen? So if I've got 4 pairs, so there's 4 I have chosen. I've not chosen tails, tails, tails. I've not chosen heads, heads, heads. What else have I not chosen? And Rowan has said none of yours have a single tails or heads in the middle. Perfect. So I've also not chosen alternating. So I think that kind of sums it up. So I've chosen 4 of them lots of times, and 4 of them I've not chosen at all. And I've always got like 2 together. So I've got 2 heads next to each other or 2 tails next to each other. Never one on its own, and never 3 in a row, which I think is pretty much everything that everyone's saying. So we're going to move on, and some really good reasons why I've not chosen 3 in a row. Or alternating, and so I'm going to explain that now. Let's have a think about the maths of this. So I'm stopping looking at the chat now. So imagine you chose tails, 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 as some of you did. Then I chose heads, tails, tails to play against you. And in this game, tails, 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 which you chose, will come up at some point, as if you flip that coin enough, right? So if you flip the coin for long enough, at some point tails, tails, tails will come up. But the question is, what must precede that first tails? What must come before it, if that's the first instance of tails, tails, tails? And the answer to that, of course, is heads. Otherwise, that wouldn't be the first tails, tails, tails. And now you can see that I have very sneakily, I've just snuck in and got my sequence before you have a chance to have your third tails appear. So heads, tails, tails sneaks in before you get your tails, tails, tails. And this is always going to happen. So I'm always going to sneak in with my heads, tails, tails, and always beat you if you choose tails, 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 unless, and some of you will have spotted this, unless tails, tails, tails happens at the very start. So that's the only way that you can win with tails, tails, tails. And what's the chance that the first 3 coin flips are tails, tails, tails? Well, there are 8 different options, and each of them are equally likely if you're just flipping the coin 3 times. So therefore 1 out of 8. So there's a 1 out of 8 chance that the first 3 coin flips tails, tails, tails. So you had a 1 out of 8 chance of beating me if you chose 3 of the same. And you know that probabilities add up to 1. So therefore I had a 7 out of 8 chance of beating you. So I had an overwhelming advantage if you chose 3 of the same. For the other games, I didn't have quite such an advantage. You can see the chance of you winning here now on the left-hand side. But in general, on average, I had a 3/4 chance of winning. So 5-3, I did slightly worse than we might expect me to do, but I still won. The maths of the other games is a little bit more tricky. Number 3, the same situation. You need to use conditional probability and all sorts of tricky things. And there is a big link that I'm going to give you at the end, a link to my website, which has got all sorts of different videos from different people on it. And some of those videos will go through the maths of those other games. So you can go and have a look at that and work out why you had a third chance of winning or a quarter chance or whatever, based on the one that you chose. But before we move on, I'm sure some of you want to know what my strategy is so that you can go and fool somebody yourself. And the answer to that is, of course, step number 1, make your opponent choose first. So they have to go first. That's really essential. And then take their first 2 coin flips and make that your final 2 coin flips, like I did here. And then I'm taking their middle coin flip and I am reversing it and making it my first one. So the middle one here is tails, reversing it gives you heads, and that's why I've got heads at the start. So that is the strategy. Go and fool somebody. This is actually quite a famous game, and it's called Penny Ante, or Penny's Game, where Penny is the surname of the person who invented this game. Nothing to do with the fact that you're flipping a penny. That's just a weird coincidence. A freaky coincidence, if you like. There we go. To do with the title of the talk. And I think this is counterintuitive. I think people tend to expect that it doesn't matter which of the 8 sequences you choose, and that would be true if we were just flipping the coin 3 times. But we're not. As soon as you start continuing to flip that coin and playing penny ante instead, then everything changes. And so we've got our first counterintuitive game. If you think you recognise it, you might have heard other mathematicians talk about it, or you might have seen TV magician Derren Brown play this game in one of his shows, and he used it in order to make a group of people feel like they could control the flip of the coin, like that they somehow, their thought processes could influence the flip of the coin, which of course is nonsense. Actually what he was doing was using some maths and making one team come out as the winner more all the time, and they felt that it was the kind of their brain power which was doing that, which is pretty fun, and it is in the list of videos that you'll be given at the end of the talk. So definitely go and watch that. So that's Penny Ante. So our second game, which you are going to play, involves not coins, but involves some dice with some curious properties. So I've got 3 dice, a green one, a blue one and a red one, and they are not normal dice. I mean, they're normal cubes, but they don't have the numbers 1 to 6 on them. They've got some different numbers that I'll show you in a second. And the game you play with them, you have 2 players. Each player chooses one of the dice. They roll the dice, and whoever gets the highest number wins. So very simple game. But the question for you is, which is the best dice to choose in this game? And you can use any method you like to decide. So I say any method, so you could think about the probability theoretically, and in order for you to do that, I'm going to need to tell you what the numbers are. So here are the nets of those dice, so you can see what the numbers are. I think that the 4 at the top of the red is slightly obscured by my face, so that's a 4 at the top of the red one. Or alternatively, if you don't want to look at it theoretically, you can look at it experimentally. So unless you knew what was coming up in this talk, you probably don't have those special dice in front of you. So we've got an interactive version of this game that you can go to. The link for that is at the bottom there, and as you were told at the beginning of the whole talk, you can, if you've got your own device and your teachers have allowed you to do this, then you can go to that link on your phone and play on your phone. Alternatively, teachers, you can play as a class. You can just minimize the call for a bit, go to that website and play the game lots and lots of times. But before you do that, I am going to get rid of that link very quickly. I think that link will be appearing in the chat as well anyway. But I'm just going to get rid of it so that I can show you what it looks like when you go to the website, because it's not the most intuitive of websites. It's a great website, and actually if you go and play around on the website you end up on, it's a mathematician from America has made this interactive for us, and he's got all sorts of other exciting things on there, so do go and play around with the other ones at some point. But there's a few stages you need to step through to get to the bit I want you to get to. So this is what it will look like. First of all, choose your language, whichever one you want, and then you are choosing the first game. So 1 dice from 3. Then you get to choose whichever colour you would like. So I don't know, let's do blue. I don't know, blue against olive green. There we go. And then you can play OK. And then you can play the game. So you just choose 2 colours and play them against each other. As you know, the more trials you do, the closer that experimental probability will follow theoretical probability. So just keep playing quite a few times and see what happens. I'm probably going to give you, I don't know, maybe 3 minutes or something, not a huge amount of time. So I think you probably have time to investigate one pair, right? So whether it's theoretical or whether it's experimental, just pick a pair of colours and see which of those ones would win. And then what I'm going to do is I'm going to take everyone's conclusions and bring them all together and make a mega conclusion afterwards. And so you can tell me in the chat, whether you're a teacher or a student, what you found out. So like you could write, I've just played red against blue and blue beat red or red beat blue, whatever it is that you're doing. So tell me your conclusions in the chat and I'll pull them all together in about 3 minutes. There you go, it's 3 minutes of thinking. Okay, let's have a look at the chat and see what we've got coming in. So Rowan, thank you very much, Rowan. Shout out to Rowan, has said that they have found that olive green beats blue. I don't know if you agree with that. You can write into the box if you think you agree or don't agree. And they've also said that they think red beats blue. Oh, and then they've said, whoops, blue beats green. Okay, so I mean, I don't know if this is right or wrong, so you just tell me what evidence you've got as well, and we'll see what you think collectively in a minute. Thank you very much, Rowan. Anyone else, if you've got a conclusion theoretically or experimentally, stick it into the chat. Okay, fab. We've got a few more conclusions coming in. So Angela McConnell says that they think red beats blue. They've played 20 games. It's nice if you tell me what evidence you've got. That's good. I'll just take your word for it. 20 games feels conclusive, doesn't it? If you play 20 games, is that statistically significant? Hopefully. Okay, so I'm going to give you probably another. How long have I given you? Maybe like another half a minute or so. Half a minute to, as I say, you might not have time to investigate each pair. So there are 3 different pairs that you can look at. Whatever pair you're investigating, stick your conclusion in the chat. Okay, right, so final 10 seconds. I'm going to write some of these conclusions on my board. Final 10 seconds to finish off what you are doing. Okay, right, so I'm going to whiz. I'm going to whiz to my camera, and we can stop investigating, so stop playing whichever game you're playing or thinking about maths, and let's have a look at my board. So you can see here I've written down some of the conclusions that we've got. So quite a few people said that red beat blue. So they did a load of experiments, they found red beat blue, or they thought about it theoretically. And then we also had blue beating green, right? And so I guess usually what I would think at this point, if red is better than blue and blue is better than green, then I'm going to think, well, red is therefore better than green, right? So that's my intuition, intuitive thinking. My intuition would tell me red is better than green. But in fact, as some of you have discovered, that is not the case in this game. So in fact, green beats red. And so when I asked you what's the best dice to choose, that's a little bit of a misleading question. It's a little bit of a trick question, because what we've got, instead of there being one best dice that is best in whatever situation, we have got a cycle, right? And actually what's best depends on what your opponent chooses. So this again is another game where you benefit from letting your opponent choose first. So I'm just going to show you what that cycle looks like. So you've told me that red beats blue and blue beats green and green beats red. So we've got this cycle, and this sort of cycle is called a non-transitive cycle. And other games are non-transitive. So rock, paper, scissors, you might be thinking of, that's non-transitive. And you've just got to let your opponent choose first. So if your opponent chooses green, then you're going to go for blue, and so on. Some of you will have done this theoretically rather than experimentally. And a way you could do that, so you could use a sample space diagram, nice and simple. So here I have, I've effectively thought about all of the 36 possible different outcomes in this game. And if that outcome would lead to a red winning, I've coloured it in red. And if it would lead to a blue winning, I've coloured it in blue. And you can see here in this example that more than half of those 36 games lead to red winning. So red beats blue, and then the next one, then green has a higher chance of beating, blue has a higher chance of winning against green, and then green has actually an overwhelmingly high chance of winning against red. So you could use theoretical probability like that. These dice are invented by James Grime, a mathematician who's on Numberphile quite frequently. If you've not watched the YouTube channel Numberphile, I advise that you go and do that. So it's just amazing. So little nuggets of all sorts of interesting bits of mathematics. Probably 15-20 minute videos. If you've never watched Numberphile, go to YouTube, go to Numberphile, and I don't know, dedicate 20 minutes of your life over Christmas to watch a Numberphile video, and you will be hooked. So James Grime is on Numberphile quite a lot of the time. He's a famous YouTuber, and he invented these dice. But what's really amazing about these dice, called Grime dice after him, is that there are not actually just 3 of them, as some of you will have discovered when you played the game. There were some other options, and those options referred to all 5 dice. So there are actually 5 dice, and those 5 dice make a cycle as well, which is just awesome. And so your opponent chooses yellow, you choose green, and so on. So we've got 5 dice. After a while, your opponent probably will get wise to the fact you're always letting them choose first. So they might say, well, you've got to choose first this time. And so then if you're made to choose first, that is still okay. You can say, that's fine, okay, I'll choose blue. And if you choose blue, then your opponent will probably choose red, whatever you choose. So you choose blue, they choose red, for example. Then you can just say, okay, that's fine, but we're going to play with 2 dice, because if you play with 2 dice, that cycle reverses, which is just really cool. And so now you are in the advantageous position again. So it's amazing. If you add up the 2 scores on the dice, then the cycle of non-transitivity just reverses, which is really cool. But what's also really exciting, the third and most exciting thing about these dice, is that there's not only 1 cycle, so there is actually 2 cycles. So you can play against 2 opponents at once. So let's imagine that one of your opponents chooses blue and your other opponent chooses yellow, then you want to go with red. Because then you've got an advantage over both of your opponents. And there are 2 cycles even in the 2 dice situation. The only difference is the outside one changes direction. And one of the, I think that you can see the line without the arrow on it, that just means they're equal. So red and green are equal in the middle purple cycle in this situation. Some of you might have noticed from that game that we didn't call green green, and we called green olive green. And there is a reason for that, which is that you can use these names to help you remember those amazing cycles. So that you can make the right choice in the heat of the moment of the game. So the outer one is quite clearly the length of the word, right? So red beats blue, blue beats olive, and so on. The inner one is alphabetical. So I now have to remember my alphabet, which is more difficult than it sounds. So blue goes first, then we go to M for magenta, then O for olive, and that's why that's not green, right? So blue, magenta, olive, red, and then yellow. So this is just amazing. There's an amazing invention. And there's all sorts of stuff in the website link that I'm going to give you at the end, including a place that you can buy these. So if you want to buy these, so I work for Matt Parker. Some of you will have heard of him. You might have seen him on Numberphile or on his own stand-up maths YouTube channel. And he also runs Maths Gear, which is an online website for selling all sorts of nerdy toys. And we sell these. So we sell them in class sets and we sell them in mini sets. I'm not here to sell stuff, but they are great. So I'm just telling you. But also on our Think Maths website, which is the organisation that I go into schools with, we have made nets of these dice too. So you definitely don't have to buy a class set to use these with your students. You can print out the nets and then you can roll them physically as well. So you don't have to buy them. We've also got nets, and that's coming your way at the end of this talk. And all sorts of resources as well to do with sample space diagrams and that kind of thing. So this is Grime Dice, so definitely check that out when you get the link at the end of the talk. Counterintuitive for sure. I think we're all kind of imagining that there is going to be a best dice. Okay, so I'm just having a little look at the time and deciding what we're going to do next. So I think we've got a little bit of time before we move on to the lottery, which is going to happen at the end of the talk. As I said, we're going to find out what the two winning numbers are, and we're going to find out who the winner is. So we've got a little bit of time before that's going to happen. So I'm going to finish this little section before we get to the lottery by telling you a story. Okay, so this is a story about freaky probability. It's a story about coincidences, and it's a story about these people here. Right? It's a story about this girl here with the arrow. And so this story is about her and her holiday. So you can see that she's on holiday I think she's in Disney World in Florida. She's about 5 years old when this photograph is taken, and her name is Donna. Right, so Donna is on holiday and she's with her two brothers and Smee. That's who's in the photograph. She's on holiday, and basically she went to university when she was about 20, and she was actually from New York. So she grew up in New York and she traveled a long way to go on holiday when she was 5 to Florida. She went to university when she was about 20, and she met a man called Alex. And Alex was from Canada originally, and they went on to get married. So when they were about 25, they got married. And at their wedding, as lots of people do at their wedding, they had pictures of them when they were children. So they had some pictures of Alex when he was a child and some pictures of Donna when she was a child. And she chose this photograph. And this was the first time that Alex had ever seen this photograph. And he looked at it and he said, hang on a minute, that man looks like my dad. Hang on, that is my dad. And therefore, that's me, right? So this is a true story. So somehow they had both managed to be photographed together 20 years or 15 years before they went on to meet, 20 years before they went on to get married, managed to get photographed together as children. They didn't know each other at this point. As I say, Donna was from New York, Alex was from Canada. They both happened to be on holiday at the same time, exactly the same photograph frame, when they were 5 years old, which is pretty amazing, right? And so when you tell people this story, people go, oh my gosh, what are the chances? Which is, is that question I was talking about at the start of the talk. So is this mathematically interesting? Well, this newspaper thought so. So this is a newspaper from Canada. You can't read this, but down here it says, the odds are astronomical. So they said the odds of this happening are astronomical. Now, I agree that the odds of this happening specifically to Donna and Alex are really tiny, right? So the chance of it happening to them specifically, astronomical, fair enough, whatever. But the chance that this would happen to someone somewhere in the world, I disagree that that is unlikely. I think actually, I think we'd expect that to happen. I think it's pretty likely that this would happen to someone somewhere in the world, which is what actually they're saying in this article. So essentially, if you think about it, 7 billion people in the world. So in the order of a billion people. So let's say that Donna could conceivably meet and go on to marry, I don't know, something out of maybe a billion people, maybe a billion possible choices for who she could meet to go on and marry. And let's imagine she's only ever in one childhood photograph, and that's this. And I know that's unrealistic, but we'll come back to that in a second. Let's imagine she's only ever in one childhood photograph. Then the chance that the one person of the right age in the background of that one childhood photograph is the person she goes on to marry is like 1 out of a billion, right? Really tiny, 1 out of a billion. But then we've got to remember that there are in the order of a billion people all in the world that this could happen to. So if you've got a billion people all trying to do something that has a 1 in a billion chance of happening, then we'd expect that to happen to one person. But actually, she's not just in one childhood photograph, she's probably in hundreds, maybe thousands. And actually, these days, you're probably in tens of, when you were children, you're probably in tens of thousands of photographs. So we wouldn't expect it to happen to one person around the world, we'd expect it to happen to hundreds, thousands, tens of thousands of people around the world. So although this is very special and romantic for them, I don't think it's really news, right? I don't think this is really mathematically interesting. And I think it's one of those moments when our intuition doesn't really agree with what mathematics says. So I think we are coming to the time we're going to have a think about the lottery. So while I'm changing my view, 10 numbers, you choose 2 in your head. Can you decide what you think your chances are of getting the winning numbers on the festive lottery, not festive lottery, lottery today? So what do you think your chances are of getting the winning numbers? And I'm just going to whiz my slides up, let you have a think about that. You can use a calculator if you want to. Some of you will be immediately going for a particular button that you learn about at A-level, I imagine. What are your chances of getting the winning numbers on my micro lottery? Okay, so my micro lottery, there is a reason I've called it my micro lottery, possibly a clue, we'll see. And your chances of winning, one way we could work that out is we could say, let's work out how many different possible pairs there are that you could choose in this lottery. How many different possible pairs you could choose? Okay, so well, we could start by saying, well, there are 10 different ways that you can choose the first number. And once you've chosen that first number, it stays out of the machine, as I said earlier on. So that means then there are 9 ways of choosing that second number. So you might be thinking 10 times 9 gives you 90. And that's really good thinking. But as some of you will have spotted, that 90 includes some of those outcomes twice. So it will include 1 and then 2 as something different from 2 and then 1. And as I said earlier on, the order the numbers comes out of that machine doesn't matter at all. So I'm going to take that 90 and I'm going to divide it by 2, and that's going to give me 45. So there are 45 outcomes in this lottery. So if you thought 45, good work. So therefore your chance of winning is 1 over 45, because each of those outcomes is equally likely to come up. You could have got this a different way. So you could have thought about probabilities, you could have thought about n choose r, or you could have written out all of the different pairs systematically, which I've done here, right? So you can have 1 with 2 or 1 with 3 and so on. And if you do that, you get this kind of lovely little triangle, which I really like, which actually means that 45 must be a triangular number, because we're doing 9 plus 8 plus 7 plus 6 all the way down to 1. So nice triangular number. And those of you who have learned about the choose function and n choose r at A-level will maybe know that anytime you do something choose 2, you get a triangular number, which I think is kind of nice. And so you've probably seen Pascal's triangle. You might have noticed that the choose 2 row always has triangular numbers in it. Anyway, lots of really nice maths going on here. So lots of different ways to get to the answer, but there are 45 outcomes. So you've got a 1 in 45 chance of winning my lottery. So probably, like, I don't know, what's that? It's a bit more than 2% is your chance of winning my lottery, which isn't tiny, right? You might win. What about your chances of winning the real national lottery? You've got to do the same idea. This time you've just got to work out how many different ways there are of choosing 6 numbers from 59. So that's your challenge for afterwards. You can do that if you want to. You could obviously use nChooseR, but there might be some more intuitive, interesting ways of getting there too. And if you do that, then you will discover there are not 45 ways of choosing those numbers. There are about 45 million different ways of choosing numbers on the National Lottery. And so therefore your chances of winning my micro lottery today are about 1 million times greater than your chances of winning the real National Lottery, which I think is an important message. Suddenly my micro lottery looks a lot more generous, which is why I've called it micro, of course. So micro 10 to the -6. Micro means a millionth, right? And you've got a millionth of the chance if you play the real National Lottery. Anyway, I think it's hilarious. So it's the micro lottery because you're 1 million times more likely to win my micro lottery than the real National Lottery. But just like in our micro lottery, the numbers you choose on the real National Lottery will not affect your chances of winning, however counterintuitive, however freaky that feels. And so I'll just show you some groups of numbers on the real National Lottery, because at this point, when I show people these numbers and I say they're all equally likely to come up, I get quite a response that is the same amongst almost everybody, which is, really, what about B? Surely Group B is less likely to come up. People say, I've just never seen Group B come up on the National Lottery. And they're right, Group B has never come up on the National Lottery in this country. But also Group A and Group C have never come up on the National Lottery in this country. I mean, most of the 45 million have never come up on the National Lottery in this country. And it's just that when you look at Group B, there's a pattern, and that makes it memorable to you. And Group A and Group C don't have a pattern, so they're not memorable. They look a lot like other groups of numbers, which kind of tricks your brain into thinking that they are more likely to come up. But it's not true, right? They're all equally likely, and if you hang around long enough, something with a pattern will come up, as it did literally last week. How exciting. So in the South African lottery, we had 6 consecutive numbers. That group of numbers, no less likely to come up than any other group of numbers. And so those numbers alone are not a reason for us to think that there is any fraud going on. Really nice that happened last week. But just because the numbers you choose will not affect your chances of winning the lottery, that doesn't mean that there's no strategy that you could have employed today, or not today, whenever you filled in the Google form when you chose your numbers. And to explain that strategy, I'm going to tell you a story about these numbers here. So first of all, there's a pattern. Good work if you spotted that they are all multiples of 7, apart from 41 on the end, of course, which is not. And in the same way, people really like the number 7. People really, really like multiples of 7. So much so that about 4,000 people matched the 5 multiples of 7 here. And that means that they had to share the pot of money that was allocated for matching 5. This is in 2016 when they were the rules in the National Lottery. And so instead of getting about £1,000 like you'd normally expect for matching 5, they got just £15 each. Which they were understandably a little bit upset about, but it was fair. And so the moral of this story is that if you choose popular numbers in the real lottery, chances are if you win, you'll have to share your money with other people. Whereas if you choose unpopular numbers, then you will, if you do win, you'll stand to win a higher amount. If you chose unpopular numbers on the Google form, then you might be the only person with those numbers and you won't be put into a virtual hat to see if you're the winner or not. If you chose popular numbers, chances are other people did too, and you might not win even if you get the winning numbers. So that's the moral of this story. It pays to choose unpopular numbers. Which numbers are unpopular? Well, because I closed that form before the start of the talk, I was able to analyse your results. So this is the graph of the numbers that you chose. You're predictable. Well done. 7 is your favourite number. 10 is your least favourite. Also not a huge surprise. So people really don't like the numbers at the ends of the range. 5 was interesting. 5 is a bit of a surprise actually, because people usually like prime numbers. So I was kind of surprised by that. So well done for going against the grain. So these are the numbers that you like and don't like. But what are the 2 winning numbers in today's micro lottery? Let's find out. So it's now time to remember what numbers you chose and get very excited about the possibility of winning a mathematical prize, or just winning the pride of knowing you've got the right 2 numbers. So this is my machine, and I'm just going to whiz this up a bit so we can see that a bit better. There we go. So I'm going to give this a whirl, and we will hopefully get, which way do I do this? I was trying to remember that bit, there we go. Okay, so you can see that one of them has come out by accident down here, but that's still random. I didn't know which one would come out by accident, so I'm just going to take that. That's fine. So we have got our first number. If you're ready, drum roll around the country. So the first number on the Micro Lottery 2020 Christmas Lectures is 3. So if you chose 3, you are still in the game. Still in the game if you chose 3, and then you can see that there is one here ready to come out the traditional way. So I will let that one come out, and that's going to be our second number. I'm going to put my hand here. Oh, I've managed to put that back in by accident. So that you can, here it is. There's 2 here that come out, so I'm just taking the first one of the 2 that came out. And the second number in today's lottery is the number 1. So if you got 1 and 3 or 3 and 1, then you have got the winning numbers. Doesn't matter the order that you chose them in. And I have got, if you can bear with me, a spreadsheet in front of me telling me who my winner is if it's 1 and 3. Now, there were a few pairs of numbers that didn't have anyone choosing them. So in that case, the spreadsheet has randomly chosen someone who got either 1 or 3. But we'll just see if we did actually have a winner for 1 and 3. And let me just very quickly check. So actually we didn't. So 1 and 3 was one of the ones that nobody chose. So nobody chose 1 and 3. So my spreadsheet has randomly given me a winner for somebody who either got 1 or got 3. And that winner is Toby Croft from Cedars Upper School. So well done, Toby Croft. You're going to be getting a prize in the mail that I imagine probably will land with you after in the new year. It'll probably be sent out next week, so it'll probably get back to you in the new term. Great work, you're my winner. Well done anyone else who actually got 1 and 3 if you were just playing along with paper. And that brings my close close to the end. So we're going to have some questions afterwards, but hopefully you've seen some things that you can play with at home. There are all sorts of links that I'm going to show you now. So actually, if we just whiz back to my slides, I can show you that. So this is my big mega link of links. So that's our website, Think Maths. Teachers, I do all sorts of talks in schools, so go and have a look at that on our website if you're interested. And so if you go to that link, I think it's also being put in the chat. There's videos, there's all sorts of things to do with what we've looked at today. Otherwise, thank you very much for watching, and I'll hand back to Kalsu because we're going to have some questions now.
Well, thank you, Zoe. It was such a fun and wonderful presentation. I'm sure all our attendees have loved it as well. And now it's time for questions. So if you have questions for Zoe, please send them to us via chat. And while we receive your questions, I just also wanted to put a final request to you all, well, the students and the teachers, that we have a survey for our listeners. So if you can please complete the feedback form that we are sharing in the link in the chat box, then please ask your students to do this individually, and then we'll be really happy to receive your feedback on our event today. And that then brings us to questions for Zoe. We have the first question, that do you play the lottery yourself?
Okay, that's a really nice question. Do I play the lottery myself? I tell you what, I'm just going to get that link off the screen so you can actually see my face. So I have played the lottery. I don't play it continuously. So I've played twice in my life. And so the first time I played was when I was first legally able to do so. And I actually can't remember if that was 18 or 16. I think it's changed recently. But whenever, the day of my birthday, whenever I was allowed to first do it, I went and bought a ticket. That was kind of fun. Didn't win, as you can imagine. And then the second time I played was in 2015. There was a time when the expected return of the lottery ticket was greater than the £2 that you spend to play the lottery. So you can work out the expected return by multiplying the probability of you winning a prize by the prize that you get, and then summing all of those for all the different prizes that are possible. And it's got even more complicated to work out the expected return recently, because they've introduced other things like Lucky Dip and kind of they've got a raffle now where there will always be a winner of some sort, even if it's not the jackpot. So it has changed. But in 2015, there was a point when so many people had bought tickets that increased the prize money, which meant that increased the expected return. And then people heard about it, so then more and more people bought tickets, and it was just kind of like a snowballing effect. And so the expected return was greater than £2, and I don't think it's ever happened since. Especially now, the expected return has decreased since they changed the rules in, I don't know, whenever it was, a few years ago. So that was the second time I played. The mathematically sensible day to play the lottery was the second day I played, and I also didn't win. There we go. I mean, some people play, I guess it gives money to charity, doesn't it? But don't rely on it as a method of making money is my only real line of advice.
So the second question we have is, what's your favorite game to play which uses freaky probability?
Okay, so what's my favorite game that's counterintuitive, essentially? I do like Penny Ante's, the one that we started with, because I think when you tell people just choose one of these 8 sequences, even if you explain the game to them beforehand, I think your gut reaction, I think, is, well, they're all, there's eight outcomes, they're equally likely to come up, so it doesn't matter what I choose. But when you think about it in more detail, like we did, then you realise that there's more to it than that, and that's not the case. So I think probably that one. I do like that. I mean, if I was really mean, I could play it to make money. So I could play lots of different people and tell them they've got to choose first. If they win, then I will give them 50p, and if I win, they can give me 50p. And although I might lose, I don't know, I'll lose a quarter of the time, right? So I will lose sometimes, but if I play enough times, I can take advantage of that slight edge that I've got and make some money. So if I was really mean, I would do that, probably. I'm not suggesting you do that. I'm not encouraging gambling.
Thanks, Zoe. And that brings us to the end of this year's Christmas lecture. If you also want to thank Zoe for the talk, then please do so in the comments box. And thank you all for attending, all the students, and our special gratitude to the teachers for organizing these for your students. And on our OU side, I would like to thank everyone who helped in organizing this. So Charlotte, Tracy, Katrina, and especially our broadcast team. Thank you all. Have a Merry Christmas and Happy Holidays. Bye.